Hello friends, good morning everybody. This is Professor Naveen Rathee from the Department of Electronics and Communication Engineering of IIMT College of Engineering, Greater Noida, Uttar Pradesh. Today we are here to deliver a talk on operational amplifier practical applications. So when I say operational amplifier as a practical applications, just a minute, let me share my screen. I think the screen is visible to all. So today we are going to talk about operational amplifier practical applications. Why we have chosen this particular topic is because op-amp is something which is a very high gain multi-stage DC coupled amplifier. So it can be used for amplification of both AC as well as DC signals. So that is the top priority in today electrical and electronic circuit where op-amp is playing a majority of the circuits where you will find the op-amps being used in different applications. So today my outline will be focusing rather on the rectification. We'll be talking about rectifier, half wave rectifier, full wave rectifier. Then we'll be talking about clippers. Then we'll be talking about clampers, and then we'll go with the comparators, and finally we'll conclude our session with the oscillator. So as we know that first thing is what is rectifier. So everybody knows that rectifier is an electronic circuit where we use the diodes, and some filters at the output so that the alternating cycle input waveform can be converted into pulsating DC waveform. So rectification or a rectifier is a circuit which is used for converting your alternating cycles to pulsating direct cycles, which can be further purified, which can be pulses can be further removed, AC components can be removed further by the help of using the different types of filters. So what we are doing in this rectification is we are also providing a shape to a particular signal. So when I say signals particular over here, so it means I am using a signals which are to be shaped up. So rectification is used for that particular purpose also. So first thing is in conventional method, as everybody knows, in conventional method, what we do, we generally use diodes as the major elements, and we use some resistors across which we check out the outputs, or maybe some filters if we want to see the pure DC waveform available at the output. So such type of circuits are very easy to design and use. But in conventional method, what there is a major drawback. The major drawback of such a circuit is that diode requires a minimum bias voltage for its successful operation. So when I say minimum bias voltage, so this minimum bias voltage will come from where? It has to come from the input source only. So input source voltage has to reach up to that minimum bias voltage part so that the diode starts conducting, and then further rectification process starts. So when we say this, so this there will be a drop because bias voltage has to come from the input source. So there will be a drop the input signal voltage. If I am expecting 2.7 volt and I am using a silicon diode, so 0.7 volt will be consumed for the conduction of the diode. So this is something, a drop which is has to come from the input signal voltage. So for most of the circuits in conventional methods I'm talking, these drops are neglected. Why it is neglected? Because we assume that the input voltage is very large. If you compare 2 volts with 0.7 volts, we don't consider 0.7. So in generally we see that mostly we are using this treating when we analyze them only 0.7, or sometimes to for analysis we show that it's an ideal diode, immediately it starts conducting. But in general it is not. It requires some minimum bias voltage. So here in conventional method we are neglecting those biasing voltage for comparison purpose. But when a precision rectifier, when I'm talking about, when we talk about the precision rectifier, these drops are very significant, because if these drops are available along with the DC input signal which is to be rectified, then first thing is we need to nullify these particular drops. So these particular drops has to be nullified. If these drops are not being nullified, then they can also be seen at the output of the op-amp. For such application, we generally prefer a precision rectifier. So now let me go straight to the precision rectifier. So it's clear now. With the precision rectifier means Along with the diodes and the resistors and the filters, we are also going to use the operational amplifier. So when I say operational amplifier, let me show you one circuit over here. In this particular circuit, what you see is we are seeing an operational amplifier which is converted in non-inverting configuration. Now, if I apply an input over here with V in as the input, let us say I am putting it as a sine wave as an input. If I am using sine wave as an input over the terminal V in, then during the positive half cycle, what will happen? Diode will conduct or not. During the negative half cycle, diode will conduct or not, and what will be the output available. So let us analyze it with the waveforms. So this is the input which we are giving now. This is the input which we are giving at this particular terminal, that is the non-inverting terminal of the input. So when we are giving the during the positive half cycle of the input signal, during the positive half cycle, what will happen? There will be no phase shift. The output will be as it is with the same phase, that is positive output will be available. So when this output obtained at the output of the op amp is positive, it is connected with the p type polarity of the diode, and this negative, that is inverting terminal, is connected with the negative terminal of the PN junction. So in that case, what will happen? Diode acts as a forward bias diode, and when it is acting as a forward bias diode, what will happen? It will act as a short circuit, and the current will flow through this circuit like this. When it is acting a short circuit, the entire current will flow through this, and when current is flowing through this, there will be a drop across this RL, which can be seen at the output. So what is V naught obtained now? V naught will be same as the replica of the input waveform. So you can see that the output, the same replica image is obtained at the output. So during the positive half cycle, this is something pulsating DC. Only this much of the pulsating DC is being obtained because this diode was on. Now coming on to the negative half cycle, when I apply a negative half cycle at this V terminal, so this negative will come at the output without any phase shift because I have converted a non-inverting. Same negative will be available at the output. So negative terminal is now negative is connected with the positive terminal of the PN junction diode, and positive terminal will, so this diode, what will diode will become? It will become reverse bias. So when diode is reverse bias means it acts as an open circuit. So no current will flow. When no current will flow, there will be no output obtained across the resistance RL. So V in out will be equals to 0. So you can see it from here in the output waveform. During this negative half cycle, there is no output available. So we have seen that in a precision rectifier where we have used operational amplifier for rectification purpose, the operational amplifier, this is very precise. So that is why it is called precision rectifier, where this op-amp will take care of this DC biasing input voltage, which was a drop in the conventional. So only during the positive half cycle we are getting the rectification. That is why it is called as a half wave precision rectifier. Now, if I see the practical circuitry, so we have used this circuitry, and we have used multisim software for analysis of this particular circuit. We have applied 5 volts peak to peak input sine wave with a frequency of 1 kilohertz at the non-inverting terminal of the op amp, that is mu A 741. The diode which we have used over here is 1N4148. So when this is the connection over here, same thing we have seen, 0 to 2.5 volts, diode gets on because same polarity is available, diode gets short circuited, it acts as a forward bias, and the current will flow through this, and you can get the output across this RL. When the negative cycle is there, diode gets reverse bias, it acts as an open circuit, no output is available. So the multisim waveform which is obtained using the multisim software for simulation purpose. So you can see from 0, this blue color, 0 to 2.5 volts during the positive half cycle, we are getting the output. This means the same replica of the input. During the negative half cycle, we are not getting output because diode is open circuit. So the output is equals to 0. So this is the half wave rectification using the operational amplifier. Now coming on to the full wave rectifier. So in full wave rectifier, what we have done is we are going to use 2 operational amplifiers. We are going to use 2 operational amplifiers. So in one case, we are going to use it one diode for conduction, and in other one we are going to use another diode for conduction. So let me show you the circuit. So this is simple circuitry of a full wave precision rectifier. So here we have used two operational amplifiers, A1 and A2, right? And here we are using two diodes, D1 and D2. The input will be available across this V1, and these are the feedback resistors. This 10 kilo ohm, then this 10 kilo ohm, and this 10 kilo ohm. So these act as a feedback resistor. So now how this circuit will work? So when I am applying a positive input signal over here, when I am applying a positive input signal over here, what will happen? When I am applying a positive input signal over here, that means I am talking about the positive half cycle of the input waveform. So this polarity will change because I have connected to the inverting terminal of the op-amp A1, and phase shift will be there. So the positive will become negative over here. This negative is connected with the negative terminal. This positive is connected to this 10 kilo resistor to the positive terminal, and this diode D1 gets forward bias. When D1 is forward bias, it acts as a short circuit. Now this negative terminal of the op-amp, output of the op-amp A1, is connected to the P-type, to the P-type polarity of the PN junction diode. So this diode becomes reverse bias. It acts as an open circuit. So this particular components along with this diode D2 will not be available during the positive half cycle. In the positive half cycle, only the input will be from V1 and it will go through A1. The diode is now conducting. So the diode is conducting through this 10 ohm resistor. The diode will start conducting now, and along with this 10 kilo ohm resistor, the voltage output, which was the negative, that is 180-degree phase shift output, will be available again at the inverting terminal of an op-amp A2. So when I am talking about inverting terminal of an op-amp A2, so what will happen is uh, what will happen is again there will be a phase shift. So when there is again a phase shift over here, so what will happen when there is a phase shift? Again the same phase shift will be done. Again phase shift will be done. So you go back to the again positive cycle. So during the positive half cycle, so we can say that during the positive half cycle, the signal flow is from V1, it passes through A1, passes through the diode D1 because this is acting as a short circuit. Through this 10 kilo ohm, it reaches to the op-amp A2 inverting terminal. Again, a phase shift is there. So you get the same image, whatever we have applied at the input at the positive cycle is available at the output, right? Now, if I applied a during the negative half cycle, what will happen? We see that scenario also. So when I apply a negative half cycle, negative means again phase will shift, it will become positive over here. So when it becomes positive output over here, positive is connected with the positive, positive connected with the negative over here. So now process is the reverse. D1 gets reverse bias, D2 gets forward bias. So when D2 is forward bias, the circuit will follow this particular path. So this is short circuited, the current will follow this path and it goes to the non-inverting terminal. So again, positive output will be available. So we can say that during the negative half cycle signal, the signal will flow from V1 to the op-amp A1, 180-degree phase shift. The output will be positive. Diode D2 will start conducting. Current will flow through this diode D2 and it goes through the non-inverting terminal of the op-amp A2. Without any phase shift, the same output, positive output is obtained across the output of the op-amp A2. So this is the full wave rectification. So we have seen that in both the half cycles, positive cycle or negative half cycle, the output obtained is positive in nature. So we get the full pulsating DC in both the input cycles. So if I want to draw the equivalent circuit of this circuit using the positive cycle and negative cycle, so let me show you first the equivalent circuit diagram of a positive half cycle. So during the positive half cycle, diode D1 was conducting, the upper one diode was conducting. You can see it from here. This diode was conducting. So when this diode 1 is conducting, this circuit will become like this and it will pass through 10 kilo ohm resistor. So this diode was conducting, it will pass through 10 kilo ohm resistor. This is coming positive. Diode is conducting, it passes through the middle resistor 10 kilo ohm and it goes to the inverting terminal of the op-amp A2, which gives the again phase shift and we get V0 at the output. Now, coming on to the equivalent diagram for the negative half cycle. So when negative half cycle is available over here, negative is connected with a negative. So diode D2 was conducting. When D2 is short circuited, upper one diode D1 was open circuit, so it gets cut out from the circuit. So the path which is being followed is this now. So this below one 10 kilo ohm resistor to the diode D2 and it goes directly to the non-inverting terminal of the op-amp A2, and we get positive output across the op-amp A2. So during the negative half cycle also we get positive pulsating DC output across the op-amp A2. So that is why we have connected the two op-amps. Two op-amps they are being coupled with the help of the resistors along with the diodes. So for negative, as I told you, as long as Vi is less than 0, the D1 is off and D2 is on. So that D2 is conducting, so the path of the current will be balanced. Right. So now coming on to the practical equivalent circuit diagram. So whatever we have obtained from the output, that is V1, that is the op-amp A1, whatever is the output which we have obtained over here. How you get 20 kilo ohm? You see it over here. This 10K and 10K, they are in series now. So it becomes 20 kilo ohm. So this 20 kilo ohm, I am showing it over here at the terminal, this terminal number 3, which is connected to the inverting terminal of the op-amp A2. This is what I have shown over here. So this 20 kilo ohm is there now. So this 3 is connected to the inverting terminal. To the positive terminal, what we have got is we have got negative cycle we are giving. So we have got 2/3 of the input voltage, that is Vi. So what will happen now in this particular circuitry, using the gain formula for a non-inverting terminal, which was 1 plus Rf by R1. Rf was the feedback resistance. This is the formula which we are using. 1 plus Rf by R1. What is the feedback resistance? That is R, 10 kilo ohm. What is the input resistance? 20 kilo ohm. That is 2R. So 1 plus Rf by R1 becomes R by 2R. So RR gets cancelled. You get 3 by 2. 3 by 2 gets cancelled with the 3 by 2, and the output which is obtained is minus Vi. So it means whenever the input is in negative half cycle, you will be getting the positive output waveform. So whenever Vi is less than 0, it means during the negative half cycle, the output is getting positive, right? So you are getting in both the cycle, positive or negative, we are getting the positive pulsating DC in both the cycle. Hence it is named as a full wave precision rectifier. And then we have seen a particular circuitry and we tried to simulate it in the multisim software. So this is the actual waveforms which we obtained in the multisim. So this green color is the input sine wave, and over the above this blue color which has taken over as the output. This is the output. So you see in the negative half cycle also we are getting the positive output. So in both the positive as well as the negative we are getting the positive output, right? Now coming on to clipper. What is the function of the clipper? The function of the clipper is to clip a certain portion of the input signal waveform, right? And the remaining portion is not to be clipped off. So it means whatever portion is clipped off, that will be seen as a clipped output in the output waveform, and the remaining portion which was available in the input, which was not being evaded, will remain as it is in the output. So clipper is a circuit, is an electronic circuit rather, which is used to evade the output of a circuit to go beyond the preset value, that is voltage level, without varying the remaining portion of the input waveform, and hence they are being named as clipper circuit. So in general, when we talk about clipper, what is the functions of the clipper, why we do clipping? So for wave shaping circuit, for wave shaping signals, we require clipper circuit. So we can clip a particular portion and we can give a different shape to the input signal. So that is why clippers are being used for signal shaping. So if I am clipping only the positive, now the new term has come, positive clipper. If I am clipping only the positive half of the input signal, maybe some portion or the entire full input wave, positive waveform, then this circuit will be called as a positive clipper, whereas the negative half portion will remain as. So that is positive clipper. So here again we are going to use operational amplifier for clipping purpose. So you see it over here now. This is an operational amplifier. This is an operational amplifier which is connected in non-inverting configuration. So the input which is need to be clipped off will be given over here. So there will be no phase shift because I have connected to the non-inverting terminal. So positive half cycle will come as it is at the output, and when positive half cycle is coming over here, the diode gets open circuit because it is reverse bias. Because positive is coming, positive connected with the cathode, diode gets reverse bias. When it is reverse bias, means it acts as an open circuit. So what you will be getting at the output? At the output, you will be getting the voltage. What at the output you will be getting the voltage? at the output you will be getting the voltage which is being set by this V reference voltage. So any voltage which is less than the V reference voltage, any voltage which is less than the V reference voltage will be available at the output. Any voltage greater than V reference voltage which is being controlled by the help of this potentiometer and positive DC biasing voltage, that is VCC. With the variation in the resistance value, I can control this V reference. So this V reference will define how much portion of the input signal needs to be clipped off. So any voltage greater than V reference will be clipped off. Any voltage less than V reference will be seen as it is at the right. Now, if I say negative half cycle, when I say negative half cycle, it means negative will come over here. The diode will act as a forward bias, it acts as a short circuit. And when diode is acting as a short circuit, what is the meaning of this is the current will flow through it, and when current will flow through it, the circuit will come closed, and the input which is available over here will be seen at the output without any clipping. Right. So let me show you with the waveform. Now let us say this is the input AC signal sine wave which we have given over here at the non-inverting terminal. V reference is being fixed. This is the lower value, that is V reference which we have fixed. So any voltage greater than V reference is being clipped. This portion has been clipped. So you are not able to see the portion which we have clipped at the output waveform. But the remaining portion is seen as it is. So positive portion has been clipped, therefore it is called as a positive clipper. Now if I change only the connections of the diode, I reverse the diode now, I reverse the polarity of the diode, then the circuit will clip the negative portion. So then another name will come which is called as a negative clipper. So what is a negative clipper? Negative clipper circuit is like this. I have just changed the polarities of the diode. Earlier positive was this side, negative was this side. So here now positive is this side, negative is this side. So now you see over here with the waveforms also I'll show. So during the positive half cycle, 0 to 2 volts if I am going, that is maximum peak value. Positive is coming over here, so output will be positive. Diode will be forward bias. When diode is forward bias, it acts as a short circuit, entire current will flow and entire input signal will be available at the output, which you can see in the output waveform from 0 to Vm, that is 2 volts. If 2 volt is the input over here, you get maximum over here. Now, if the phase is now start, if the input voltage is now decreasing, so it is moving now from 0 to minus Vm. So when it is moving from 0 to minus Vm, so it means output will be negative. When output is negative, what will happen? D1 will act as a reverse bias. When D1 is reverse bias, it acts as an open circuit. So when there is an open circuit, what will be the output available? Output available will be only this reference voltage, which is being controlled by the negative DC bias voltage by varying the potentiometer R. So by varying this resistance value, I can control the negative DC desired level. So this is the desired level which we have fixed now in this particular circuit. So only up to here, that is as long as it is minus V reference, and anything beyond this will be clipped out. So here the negative portion has been clipped, therefore it is called as a negative clipper. Now coming on to clampers. What is a clamper? So clamper is a circuit which is changing the DC level of the input signal, where to a particular desired level, it can be positive, it can be negative, or it can be a combination of both. So in that particular case, only the total swing will be raised to a certain DC level. So it means whatever the swing is available at the input signal waveform, it will remain same at the output also. Total input voltage swing should remain constant even in the output signal also, whether you are clamping it towards the positive side or you are clamping it vertically at the bottom side. So total swing, maximum swing should remain constant. So this is meaning of clamper. So what will happen? It will get shipped either in the upside if the positive DC level is you have kept as a reference, or you can clip it, clamp it downside if you have kept the DC level as the negative one. So clamper will, what will happen? It means you are adding some DC level, and beyond which the input signal, whatever was given over here, it will clamp to that particular DC level. So without changing the outcome, right? So based on that, if you are clamping it towards the positive side, it is called a positive clamper. If you are desired DC voltage level which you have added is a negative one, the input signal will be clamped in the lower side. It will be called a negative clamper. And maybe if sometimes the circuitry is such that some portion is clamped in the forward side, some portion is clamped at the vertically down side, then that will be called as a biased clamper. So three categories of the clampers are there. One is called as a positive clamper, another is called as a negative clamper, and the third one is the biased clamper, right? Now, let me take quick examples of the positive clamper. So positive clamper is a circuit which produces an output in such a way that the input signal gets shifted vertically by the positive DC voltage. So this is one circuit. So in clamper, first thing is, which is important, is you need to have a capacitor. You need to have a capacitor along with the diodes and resistor. So this is a positive clamper. What do you mean by positive clamper? We'll see the circuitry now. How does it work? So let me say if I am applying when this diode will connect. First thing is we should know when the diode is going to connect, because when the diode is going to connect, then only the output will be available. When this diode is going to conduct, then only the output will be available. So this diode is going to conduct when you get positive output across the output of this op amp. So positive output means you have to give negative input to the negative input cycle to the op amp which is connected in inverting configuration. So if negative signal is connected over here, it will be phase inverted 180-degree and you get positive output. Diode 1, it becomes forward bias, it acts as a short circuit, current will flow, and this current will flow across this and will charge the capacitor up to the maximum voltage of the negative peak cycle, right? Once the capacitor is now charged, now when you change the phase, now it means I am moving from negative to positive phase, that is from negative to positive. So when positive cycle will come, the diode will be reverse bias, it acts as an open circuit. So what is the output available over here now? The output available over here will be the voltage across the capacitor plus the reference voltage, difference of these two will be available at the output. So we can see that in the positive clamper, in the negative cycle, diode is conducting, it charges the capacitor up to the voltage VC1, and when the capacitor is being charged over here, so you don't get anything. So DC level which I want for clamping is obtained by this V reference by adjusting this potentiometer, which is connected to the positive DC battery, right? Now if I change the polarity of the diodes, if I reverse the connection, then the circuit will become a negative clamper. So this is negative clamper. So input signal now will get shifted vertically towards the downward side. So it will be shifting towards this downward side. So in general, we can say that the input voltage, now diode will conduct when diode will conduct when you get output of the op amp as a negative. So it means you require positive cycle. So when positive cycle is there, phase will be inverted, diode will be in forward bias, diode will have short circuited, the current will flow, and when current is flowing, what will be the output? The output which will be across here, that is only the reference voltage. And when negative cycle will come, diode will act as an open circuit. So whatever is the voltage across this capacitor, that will be added into it, and the entire input signal will be going vertically down below the negative DC desired voltage, right? Now coming on to window comparator. What is the window comparator? Why the window name has come into the comparator circuit? In conventional comparators, what we see is we use as a comparator, op amp as a comparator, then we use V in some input voltage, and then we compare it with a predefined value. If any voltage is less than those predefined values, output of the op amp will change or switch from high to low or low to high based on the desired voltage level which we have selected, right? But here we are now going to fix a band of the voltage or a range of the DC voltages which we need to compare. So there will be a window of the voltage sources. There will be a window of the voltage sources which we are comparing now. So any voltage between these two will be compared. Any voltage less than this, any voltage greater than that will not be compared. So this is the meaning of window comparator. So here again we are going to use two types of configuration of the comparator. One op-amp will be used as an inverting, another op-amp will be used as a non-inverting, and then we combine them to make a single comparator stage. Let me show you the circuit first. So here we have got, as I told you, it will detect the input voltage levels. It means there will be a specific band of the voltages instead of a single voltage, which can be greater than or less than with a predefined fixed voltage, right? So it will be having two reference voltages, which will be provided by these two inverting and non-inverting comparators. And the one comparator we are going to use for selecting the upper threshold values of the voltages, and one comparator we are going to use for selecting the lower threshold values of the voltages. So between these two, we are going to detect and we'll do comparison. So that is why we form a band of the voltages. That is why it is termed as a window comparison, because we are comparing only a range of the voltages, right? So these voltages, as I told you, two levels are there now, upper level and lower reference voltage. That is why it is called as the window comparator. So op-amp when we talk about window comparator, this is the circuit. Over here now what we have seen is there are two op-amps, op-amp A1, op-amp A2, and these are the voltage divider resistors, voltage divider network, where each resistor is the same value, so that the entire 0 to VC can be divided into three particular ranges. One is 1/3 of the VC, another is 2/3 of the VC, and the final is the VC. Now the op-amp A1 is connected in inverting configuration. Op-amp A2 is connected in non-inverting configuration. So now what will happen? I'll show you with the waveform. Let us say I am applying a triangular waveform to this input. So any voltage which is applied at the Vin, and if that voltage is lying in the range of 0 to 1/3 of VCC, output will be what? Output will be low, because we are starting the range from 1/3 of VCC. So any voltage less than 1/3 of VCC will not be detected at the output. So output of this window comparator will be equals to 0. So let me show you with the waveforms also. So this is the triangular waveform which we are giving over here. Maximum limit is VCC, 0 to 1/3 VCC, 1/3 VCC, 2/3 VCC, and from 2/3 to VCC. This is the maximum which here we are giving as the input. So now you can see it from here. 1/3 of VCC is with this op-amp A2 is used as a lower threshold value, and 2/3 of VC is used as a upper threshold value. So any voltage less than 1/3 of VCC will make this output of the comparator low, because it is not being detected. So you see at the output it is 0, not detected. But the moment it becomes equals to 1/3 of VCC and it starts going beyond 1/3 of VCC, now you see now this green line, dashed line, green bold line, when it is increasing from 1/3 VCC to 2/3 of VCC. So this range of voltages now, this band of voltages is being detected by the output of the window comparator. So what will happen when it is going 1/3 of greater than 1/3 of VCC? What will happen? The op-amp A1 will get activated and it will switch the output which was earlier low to high. So the output will start, and it rises up to a maximum value. It rises up to a maximum value, and the moment it crosses 2/3 of VCC, now the moment up to here only this voltage will be detected. This voltage will be detected. That is saturation. That is the maximum threshold voltage which we have reached, 1/2 of VCC. Beyond this, if I try to increase, what will happen? What will happen? Op-amp A2 will get activated and it will switch the output of this window comparator again to low. So anything beyond 2/3 of VCC up to VCC and less than, if you say the input given is maximum VCC and then further VCC starts decreasing, you cannot detect it. Reason is we are starting the upper threshold value to 2/3 of VCC. So as long as it doesn't reach to 2/3 of VCC, it will not be available at the output. So you see over here from 2/3 of VCC to VCC maximum and again back to 2/3 of VCC, no output signal is detected. So there is a window available of the band of voltages which are available at the output. So that is why it is called as a window comparator, right? Now coming on to the last application, practical application, that is the phase shift oscillator. What is oscillator? First thing is, what is oscillator? So oscillators provides the basic clock signal that is used to control the sequential action of the entire system and synchronize its various stages. Let me give a very simple example. Suppose you have designed one circuit, one embedded system, and in one embedded system you have got different types of PCBs connected, or maybe some sensors are not connected, and you expect an output at the same time delivered by all the circuitry which are involved in your embedded system. So it means all has to be synchronized, all has to work in the same clock signal. It means frequency has to remain same for the output to be there. So if that frequency is being varied, so one of the output of any hardware can lead or lag, and the desired voltages, desired expression, or the desired output scenario which we are expecting will not be obtained, and oscillations are such circuit which will provide a clock signal where all the hardware circuitry will work on the same clock signal and in a synchronized manner, right? So as I told you, oscillator doesn't require an external input sources for getting oscillation. Only the DC sources which are used for running an op-amp, that only DC input will be converting into AC output. So this output which will be obtained after the oscillation, it will be having a range of frequencies with different shapes, right? Then, as I said, amplifier, because we are amplifying the DC into AC output. So oscillator is again an amplifier circuit, but with a positive feedback, because it is a self-sustaining circuit, because it generates the frequency for oscillation purpose. So it is generating the frequency by itself. It's a self-sustaining circuit. But only thing needs to be kept in mind is it's an amplifier with a positive feedback. Why I'm telling you positive feedback? I will explain it in further slide. So there is a small feedback amplifier also. There is a small feedback amplifier also with an open loop gain which is equals to slightly greater than 1 for oscillations to start building up. But to continue the oscillation, the average loop gain must always returns to unity. So let me show you the feedback circuit first. So this is a simple circuit. So you see it over here. We are using operational amplifiers in oscillation circuit. So what this operational amplifier will do, it will, since it is connected in an open loop configuration, so it will be having a very high gain of the order of 10 to the power 6. So whatever input which we are applying over here will be multiplied by 8 times available at the output. But this output goes back to the feedback network. So this feedback network will be having some sort of the resistances, and there might be some drop across those components. So whatever losses are there in this feedback network, that losses has to be taken care by this open loop op-amp unit. So it means when we are selecting the op-amp, we need to ensure that the gain of the circuit is high as comparison to the gain of the attenuator, because of the certain losses which are being available, which have been created in this feedback network, that can be overcome by the help of this open loop gain, right? So as we know, output of this is a positive feedback, because whatever I'm applying is a positive input, and in op-amp I'm connecting it with a positive non-inverting configuration. Output will be positive over here. The same output is available as an input to the feedback network, and this will be again with the same phase will be getting multiplied by the gain of the feedback network, that is beta. So beta into V in you'll be getting. So this V becomes feedback, and this is summation circuit where we need to find out the difference of these two. So V in minus VF. VF is nothing but here beta into the voltage available across the output of the feedback network. And then this is further amplified by the open loop gain, and this keeps on oscillating, and you get a constant frequency, and we say that the oscillations are taken place, right? So as we know, when we talk about this open loop operational amplifier, so gain of this is very high. A is equals to V out by, everybody knows it. A is the open loop gain. Now, if I want to find out the gain of this entire circuitry, that is the feedback gain with the feedback, because now we have connected the feedback network also. So gain with the feedback network, what it will be? Gain with the feedback network will be equals to A multiplied by this input V in minus beta times V naught. This is equals to V naught. So beta is what? Beta is the feedback fraction. That is the gain, feedback gain. So now if we further simplify this equation, what we'll get? We'll get A into V is equals to V out on 1 plus A times multiplied by the gain factor beta of the feedback network. So now we can find the gain with the feedback V out upon V in, V out upon V in, which will be equals to GV, that is gain with a feedback network. GV, will be equals to A upon 1 plus A beta will go into the denominator, and this is the final expression of the gain with the feedback, because now it is a closed loop circuit, it is not an open loop circuit. So this gain needs to be considered for the oscillations. So these are some of the basics which one needs to keep in mind while designing the oscillator. Then another important criteria which needs to be satisfied, and it is mandatory to be satisfied, which is called as the Boxer criteria. What does it say? So first thing is operational amplifier which is connected is an open loop configuration, and that too in a non-inverting configuration, inverting configuration, it will provide a 180-degree phase shift. So operational amplifier should provide a 180-degree phase shift, and the remaining feedback network which you have connected in the feedback loop should also provide a 180-degree phase shift, so that the net phase shift across the closed loop circuit must be 0. So this is the first condition. So loop gain of the circuit must be either equal to or greater than unit, and the phase shift around the circuit must be 0. So these are the conditions for sustained oscillation, which are called as the Boxer criteria. So for initiations of the oscillation, if you supply an input signal is not any mandatory, because we don't require some input signal. Only signal which is available is the DC source which is required to run your operational amplifier. So only Boxer criteria, open loop gain multiplied by the feedback fraction, that is beta, should be equals to 1. And when this product of the open loop gain multiplied by the feedback gain is equals to the unity, we say that Boxer criteria is satisfied for self-sustained oscillations. Right. So oscillator system starts oscillating now, and while oscillating, what they do is they also amplify the noise voltage. So where this noise voltage will come now? Because you see there are some certain components in the feedback network which we are going to connect for 180-degree phase. So what will happen is these components will, in these components there will be a flow of the charges. So because of the rapid movement of the free electrons which are available in the resistors and all, which when you connect it in the phase shift circuitry, what will happen? This voltage will be a drop at that point. And this voltage, because it is acting as a positive feedback, this again will be amplified. So this motion is so random that the frequency can go up to 1000 gigahertz. So this is something which you need to take care of. So that is why I told you that the closed loop gain AF equals to A upon 1 plus A beta. So where A beta is A into B should be equals to 1, when the phase degree also must be 180 degrees. So with Boxer criteria possible, circuit can provide a well-defined sustained oscillation even if there is no input voltage available to the circuit. Right. So now coming on, I'll show you one phase shift oscillator where we are using the RC phase shift oscillator. We are going to use resistor and capacitor as a feedback network. Right. So we are following the Boxer criteria. As I told you, 180-degree phase shift will be provided by the inverting amplifier. Additional phase shift of 180 degree will be should provide an oscillation. So as I told you, greater requirement of providing the gain of the inverting amplifier must be greater than the loss which is produced by the feedback network. What are those loads? Noise voltage which are being amplified. Right. So this is one circuitry which I am showing. So here you see R and C, a combination of RC. This is a particular network. So this RC network is being connected. So there are 3 RC networks connected over here. So each RC network will provide a phase shift of 60 degree. So 60 degree into 3 networks RC, it becomes 180 degree. So that is what Boxer criteria told. Operational amplifier will provide a 180 degree phase shift, and remaining 180 degree shift will be provided by the feedback network, so that the net phase shift around a closed loop circuit must be 0. So this 180 degree phase shift will provide an oscillations. So this is RC phase shift oscillator. So the feedback network, as I told you, R and C we have connected. Combined phase shift of 180 degree will provide a frequency of oscillations. Each set of capacitor is providing 60 degree phase shift. Three stages we have connected, so we get 180 degree phase shift. And frequency of oscillation, how we calculate? F is equals to 1 upon 2 pi RC under root of 2 times the number of RC networks. N indicates the number of RC networks. So here we have connected 3, so you can keep N equals to 3, and then you can calculate the frequency. Now, if I am using only two single pole 90 degree RC phase network, so two RC phase network I put single pole, then 19 to 90, what it will become? It will become 180 degree phase shift. So with the help of two single pole RC stage also, we can generate a 180 degree of phase shift. So, but here in this particular case, stability at particular low frequency will be very poor. The reason being that when you generate a phase shift of 90 degree, when you generate a phase shift of time 90 degree, so time span will be very less. So when time span will be very fast, it will be moving very fast. So when time span is more, time and frequency are inversely proportional, so frequency will become lower. So at low frequency of oscillation, the stability will be very fast. So that is why we avoid two single pole RC stages. So this is one of the most important feature of an RC oscillator, which is the frequency stability. You need to generate the sustained oscillation, and those constant frequencies should remain as it is, even though if there is a variation in the load also. So this is something which is very important. So by cascading 3 or even 4 RC stages, so if I say 4 RC stages, what will happen is each RC stage will be providing a phase shift of 45 degree. So when 45 degrees are available, you get 180 degree phase shift, 4 into 45 degree. So stability can be further improved if you keep on increasing the RC stages, but there is a limit to the number of stages which are being connected, right? So this is all for the session today. Thank you all for watching me. You can reach out to me on my email ID. So thank you once and for all. Have a patience listening.